Hello everyone, I am Harshita Ravindra. Today I'll be presenting my research paper with Professor Jayashree Wilson Nair titled Integrating Population Surveys Using Spatial Visual Analytics. In this work, we propose a three-step workflow for integrating surveys using spatial analytic workflow using visualizations. We implement the workflow on a case study using two recent population health surveys in India to study malnutrition in children under 5. Outline of presentation today. Large-scale surveys are implemented to gather information about specific issues on population. However, conducting national population surveys for low and middle income countries with high population density becomes challenging. Some of the surveys tend to overlap in outcomes with spatial, temporal, or both scopes. Mining data jointly from surveys with significant overlaps gives new insight while preserving their autonomy. Our work shows that such an integrated analysis is beneficial along with preliminary analysis of existing national surveys to maintain new insight while maintaining their autonomy. In our work, we have used data from national population health surveys in India, namely NFHS4 and CNNS. NFHS4, implemented during 2015-16, provides information on population, health, and nutrition for women, men, and children under 5 for all districts in all states and union territories in India. CNNS, implemented during 2016-18, is the largest exhaustive nutrition survey, including micronutrients, conducted for the first time in India. This survey is focused on all children, that is, population under 18 years of age. Both surveys overlap in the coverage of nutrition indicators for children under 5. The summary analysis report have been published for both surveys, and the raw anonymized household level data is available only for the NFHS4. The focus of our study is on under 5 children malnutrition in India as recorded in NFHS4 and CNNS. We find the potential health indicators and the contextual factors for identifying high-risk regions of under 5 child malnutrition using integrated data mining from both surveys. Let us now discuss the comparable and integratable components of the surveys. Our three-step workflow consists of feasibility check, choosing variables for integration, and integration using spatial autocorrelation and clustering. In step 1, we first check if the state-wise sample distribution for both surveys are equivalent. We further check against the state-wise population distribution from the latest official census taken in 2011 in the states. We then check if there are commonalities in the survey's outcome from both surveys, which indicate that the surveys can indeed be integrated. In step 2, we look for indicators and contextual factors across surveys that can be meaningfully integrated. For this, the indicators and factors must have sufficient spatial heterogeneity. In step 3, we complete the integrated analysis using spatial autocorrelation. We use global Moroni and localized cluster maps using bivariant LISA computed using local Moroni. We look at the metadata and the overall descriptive statistics, that is mean and standard deviation, within the corresponding respondents of selected indicators and contextual factors, and available distribution data on severity within given labels from NFHS4 and CNNS for children under 5. We observed that the statistical descriptors of stunting, underweight, and wasting are comparable. Let us discuss step 1 here. Our first step is to establish the feasibility of integrating the selected surveys, region-wise grouping of the 30 states, and distribution of sample population covered in the surveys are shown in figure A and B respectively. The state-wise occurrence of stunting, underweight, and wasting given in percentages is shown in figure C. Figure C shows considerable differences between both surveys. However, given the comparable statistical descriptors, we now look at similarities we can find within the aggregate values. In addition to their absolute count, both the surveys have published data of the descriptive probability distribution of the severity of each of the malnutrition conditions, namely stunting, underweight, wasting, and anemia. Except for anemia, we also have data available in the gender and urbanization based sampled groups in addition to the total population. Hence, we find distribution distances for each subpopulation using Hellinger distance. To quantify the similarity between the indicators across the two surveys, here we observe that the state-wise distribution distances between the surveys are low, as the HTs are lower than 0.184 overall, much lower than the upper bound 1.0. We observe that isolated states show relatively higher HDs, namely Jammu and Kashmir for stunting and Uttarakhand for wasting across all population groups. This could also be attributed to the lesser number of samples from these regions. Overall, we conclude that the two surveys can be integrated given the closeness in time period of survey and distribution of stunting, underweight, and wasting. In step 1, we also observe that the distribution based on anemia severity were comparable between the two surveys. We visualize these distribution using the pie chart glyph, where the glyph sizes give the occurrence of anemia and the pie chart gives the occurrence of severity in anemia. We observe that while the overall occurrence in each state is similar across the surveys, there are differences in the distribution of severity of anemia. Given the limited data availability for anemia, it is difficult to explain the differences. Moving to step 2, where our goal is to identify indicators and contextual factors uniquely present in each survey for integrated analysis. We choose immunization record and micronutrient deficiency for indicators of children under 5 and maternal illiteracy, and poor sanitization facility for contextual factors. Given the spatial local heterogeneity in undernutrition in India, we study the region-based trends in variables exclusive to each of the surveys. Since the variable analysis is for choosing a variable for integrating surveys, we use visualization using a circular radar plots for quantitative comparisons, F for representing percentage data. The radar plot is also compact in its representation. Here, a region-wise radar plot has each axis representing a state in the region. Since Spatial local heterogeneity is a criteria for the variables we choose. We find that immunization record has limited heterogeneity given the uniform coverage for all vaccinations in states within a region and across regions. Micronutrient deficiency shows spatial local heterogeneity given within regions. We observe spatial local heterogeneity from the non-uniform pattern in each region. Example, there is a pronounced deficiency in folate in Assam and Nagaland in the northeast, in Andhra Pradesh in the south, and Madhya Pradesh in the central region. A significant deficiency in low serum ferritin, which is a primary cause of iron deficient anemia, is observed in Haryana and Punjab in the north and Karnataka in the southern region. Thus, we choose micronutrient deficiency as a variable for integration available from CNNS. Now we focus on integrating it with the data of contextual factors from NFHS 4. Our integrated analysis of survey is based on spatial statistics. The global Moroni statistics for spatial autocorrelation between common indicators in both survey for stunting, underweight, wasting, and anemia are given along with the bivariant LISA cluster maps in the figure shown. We see here that there is low spatial heterogeneity, which is statistically significant for stunting, underweight, and wasting. Our bivariant LISA spatial cluster analysis shows high-risk region when both an indicator and contextual factors have high values. Bivariant LISA between unimproved sanitization and micronutrient deficiency show high-risk clusters in western regions for folate, Rajasthan for low serum ferritin, large parts of northern central regions for vitamin B12, and Jammu and Kashmir for zinc deficiencies. Bivariant LISA between maternal illiteracy and micronutrient deficiency indicate 3, 1, 3, and 1 out of 30 states having higher prevalence of maternal illiteracy coexisting with folate, low serum ferritin, vitamin B12, and zinc deficiencies respectively. We observe that the clustering pattern in high prevalence of low serum ferritin, vitamin B12, and zinc deficiencies coexisting with maternal illiteracy is similar to the same with unimproved sanitization. In summary, we show a proof of concept of integrating existing large-scale population survey benefiting the stakeholders. The integrated findings may have been otherwise soiled within the survey but are significant when observed together. Planning joint outcomes across different surveys and mining data jointly from multiple surveys can give deeper insight together while preserving the autonomy of each survey in its entirety. We acknowledge the kind support by IBM Shared University Grant and the Mathematical Research Impact Centric Support Grant by the Science and Engineering Board. We thank you for your attention. We close the talk with the conclusion slides. We will be happy to take questions. Thank you.